Welcome to Lecture 6. We're going to start off where we left off in Lecture 5, where we talked about these shapes. But before we go to the diagram that I ended Lecture 5 with on a website, I want to go down to this diagram, and let's talk about which types of orbitals, and the types correspond to different shapes. So all s orbitals are spherical. P orbitals are dumbbell shaped, come in threes, and this will be evident in the box diagram. D's are very complex, come 5 at a time, and F's even more complex, they come 7 at a time. So notice the pattern 1, 3, 5, 7. So the thing that we have to understand is in a given atom, any atom, which orbitals are in which shells. So I'll do a screenshot of this, and now let's talk about these the atom in terms of the shells. So in review, remember we could take away from that wrong model, the Bohr model, the idea that the atom is like an onion. There are layers to it, and the layer that is closest to the nucleus, and I'm not going to draw a circle, but is the n equals 1 shell, principal energy level. And n is it's actually called a quantum number, and it designates which shell you're in. It's also going to correspond to the row on the periodic table. Anyway, n equals 1 shell, n equals 2, and so on. As you go farther away from the nucleus, the shells get larger in energy, higher in energy, and therefore actually a little more unstable. Remember, the nucleus is positively charged from those protons, and the electrons are present in these shells, but not in those rings. They're present in those crazy shaped orbitals. So which orbitals are present in each shell is covered in this table right here. So if I am talking about the first shell, you only have an s orbital. So only a spherical, which means since they come one at a time, you can only put 2 electrons in the first shell. Now you're going to see some similarities between those ring diagrams and this quantum mechanical model. You see that there are 2 electrons present in the first shell and 8 in the second shell, so that does stay with us. No rings. In the second shell, we pick up a new type of orbital, the p-type, the dumbbell-shaped ones. And since they come 3 at a time, there is a total of 4 orbitals in the second shell. And since each orbital can contain up to 2 electrons, remember every orbital in that diagram is going to be a box. So we have 4 boxes, as you will see when we go to the diagram, in the second shell. So that means we have 8 electrons in the 4 boxes. In the third shell, we pick up a new type, the D's. They come 5 at a time. So we have a total of 9 orbitals in the third shell, for a total of 18 electrons in the third shell. So when you get out here, very complex. Now this is one thing, I'm not going to give you pictures and all and dwell on it, but you notice that there's an s-type orbital in each shell. They're actually nested inside of one another. So the the 1s orbital is spherical in shape, 3-dimensional. Wrapped around it is the 2s orbital. So the 2s is farther from the nucleus than the 1s. Larger in diameter, higher in energy. The 2s electrons, if an electron is in the 2s orbital, it cannot be found here because that's the 1s orbital. Remember, we're still taking this idea of the electrons only being able to be in certain places from the Bohr model, but they're not in rings. They're in these, these wave functions. There's actually a mathematical function mapped out for those shapes. And then the 3s orbital would be wrapped around the 2s, and a 3s electron cannot be either here or here. 3s. So just want to make sure that you understand that they're all embedded inside of one another in these shells, and this is why we cannot draw a picture. We get to the fourth shell, we've picked up the last type. Now there are theoretically, there are a G and an H, but we're not going to go there. And most chemists don't deal with that at all. That's kind of theoretical. But this S comes 7 at a time. So once you get to the fourth shell, you have a total of 4 plus 5 is 9 plus 7. You have 16 orbitals. for a total of 32 electrons in the fourth shell. So once you get to the fourth row of the periodic table, you've got elements with quite a few electrons, and they've got plenty of places to go, as you will see when we go to the box diagram. When you get to the fifth shell, the sixth shell, and the seventh, and that's as high as we go in terms of the elements, the fourth shell essentially repeats itself. So you could take this out to the fifth, and it would be exactly the same. You could add on the G if you wanted to, and the sixth, and so on, but we're not going to worry about that. So just for you, and for most chemistry, for the majority of anybody would do, you can think of the fifth, sixth, and seventh shells as a repeat of the fourth shell. And in fact, the box diagram is going to show that. So let's go ahead and go there. We're going to go and learn how to put these electrons in this. On your box diagram, you have something extra. On this side, on the x-axis essentially, whoop, cannot draw straight this morning. You have an arrow. And remember what we talked about last time we were together. The nucleus is down here, right here. So as you go away from the nucleus, there are lines on this arrow. You will always have this diagram if you need it. Of course, I'm going to show you how it's all connected to the periodic table, as you will see down here, and you were given one of these long forms of the periodic table. Anyway, the order of orbitals is on this arrow. It's a little harder to see in terms of looking at the boxes, and I'm going to give you those rules about how we're going to do it. But anyway, it goes 1s, 2s, 2p, everything's about what you would expect, 3s, 3p, and then the next one after 3p. Now in the third shell there are d orbitals, as you see here, but they do not fill next. The 4s fills. So as we build the out from the nucleus, when we have that many electrons, we have to follow this order. Okay? We have to start at the bottom. We have to start next to the nucleus and work our way up. All right? That's the Aufbau principle. You must start next to the energy level 1 and work up, and you cannot jump to another energy level until that one is full. Okay? And then there are some other rules that we'll get to as we start doing this process. Alright, so we are going to be doing two things here. We are going to be doing orbital diagrams, which is essentially what this is. Now when you draw an orbital diagram, you are not going to draw this whole thing. You are going to draw them out in a straight line. So if I were drawing the orbital diagram for hydrogen, which has one electron, notice that that is selected on our periodic table here. Now I am not going to be able to select that while I'm drawing, but we'll just maybe toggle back and forth. Anyway, the orbital diagram for hydrogen is a box, a single box, and it is the 1s orbital. And we're going to talk about what those numbers and letters mean again. And so I am essentially showing where the electrons are in the orbitals. All right. So orbital diagrams are boxes with arrows. This number that's in front is the energy level. So first energy level, second energy level, those shells I was talking about, third, fourth shell, fifth shell, sixth shell, and so on. This next is the type of orbital. All right. When I draw the next type of depiction of electrons in atoms, it is going to be an electron configuration, and I'm going to lose the boxes. And I think you can see that if we had a big atom with lots of electrons, like say iron, drawing these boxes with arrows gets rather tedious. Writing the electron configuration is a shorthand for depicting electrons in atoms. So it would be 1s1 for hydrogen. This superscript is how many electrons are in that orbital. Okay, that type of orbital. All right, so there's the orbital diagram for hydrogen. There is the electron configuration for hydrogen. I won't be able to draw here, but we'll do a little bit here and then go back to the other page. All right, so hydrogen's taken care of. We start down here. We only have one electron. We put one arrow in the box. Helium has 2 electrons. Now notice both of these are on the first row of the periodic table. So they only occupy the first shell of the periodic table. So when I click on helium, it has 2 electrons, so I say, okay, got to start down here at the bottom, so 1, 2. All right? So the orbital diagram for helium would be the 1s orbital box with 2 arrows in it, and the electron configuration would be 1s2. Okay, now I'm going to talk you through a couple of those, and then I'll go back to where I can write. All right? Now if we wanted to talk about lithium, which has 3 electrons, we would click on it here, and you can do this. This website is bookmarked in the notes. You start down here, you say 1, 2. Now remember, if you have 2 electrons in the box, one arrow has to point up, one arrow has to point down. And then the third one goes in the next energy level, in that order that's depicted by that arrow on the left in your diagram. So we're now got our 3 electrons for lithium, and so its orbital diagram would be 2 boxes. The first one, labeled 1s, with 2 electrons in it, and then the second box with the 1. Its electron configuration would be 1s2, 2s1. Now I'm going to write this when we go back. I'm going to do 1 more, 2 more, and then I'll write. All right, beryllium. 4 electrons. You start down here at the bottom. 1, 2, 3, 4. Okay, so it would orbital diagram would be 2 boxes, each with 2 arrows, and its electron configuration would be 1s2, 2s2. I wanted to do, I'm going to skip over to carbon. Carbon has 6 electrons. How do I know that? Periodic table, atomic number is 6, so 6 electrons. All right, so if you click on carbon, we would start down here at the bottom, and we go 1, 2, 3, 4. Now here comes a rule. It is there's the Aufbau principle. It is the Pauli exclusion principle that says, you know, don't worry, you're not going to be tested on whose ideas was whose as long as you know how to use them. If I have these types of orbitals that come in multiples, P's, D's, and F's, you must put the electrons in one at a time. So I always tell students this is like you have 2 daughters and you have 3 bedrooms. Why make them share? Or 2 sons and you have 3 bedrooms. Why make them share when they can each have their own? So they don't like each other, remember. So it's better if they can occupy an orbital alone rather than squishing them up. A lot more repulsions that way. Negative repulse, negative. So we always put them in singles. So 1, 2, 3, 4, 5, 6. And then if you're going to nitrogen, you'd put the next one in the 2p, and then you would go back and fill them up. So if we went to neon, okay, which has 10 electrons, before I click on it, let's count it out together. 1, 2 in the 1s, 3, 4 in the 2s. The next orbital is the 2p. 5, 6, 7, 8, 9, 10. So this would be, I'm going to click on it now, completely occupied. And you will see that these noble gases that come at the end of the rows, generally, they always, not generally, fill up the P levels for any given shell, and that is actually a very low energy situation, and that's why they don't form very many compounds at all, because they are happy the way they are. All right, so let's leave here. Let's go back to where I can write down some electron configurations and orbital diagrams. Okay, I'm going to erase this. I'll leave that thing there. Okay, and given all of, oh, didn't want to do that. Sorry. Whoa. Let me play around with that in a second. A little more room there. Okay, a little bit bigger. All right, so I can't put the arrows in, but I'm going to write down what we just did. All right, in orbital diagrams and electron configurations. So, lithium. Well, let's do helium. We did hydrogen. Helium. There we go. We have an orbital diagram like this. All right, 2 electrons, done. Its electron configuration is 1s2. All right, so I'm going to draw a line here. And on this side, we'll do some orbital diagrams. This side, we'll do some electron configurations. All right, lithium, orbital diagram, 2 boxes now because I've got 3 electrons, so I need 2 boxes. 1s and the 2s. The 1s is full, and the 2s is... Now, students usually ask at this point about the arrows, how do I do the arrows? Do we always need to point them up or whatever? It's just a convention that we start off by putting, if the first one is an arrow up, it does not really matter. It's just when you have two, they have to be going in opposite directions. All right, so there's the orbital diagram for lithium. The electron configuration is 1s2, 2s1. Now, for both, you have a check. By adding up these superscripts on the electron configuration, it should add up to the atomic number, which in the case of lithium is 3. Does not want to go outside of that space. Can I make that bigger? I don't think so. So it's 3. And the orbital diagram, same thing, count your arrows, it should add up to the atomic number. All right, beryllium, much like lithium, 2 boxes, because that 2s was not full, so I can put another arrow in there. And so there we go with the orbital diagram. Okay, and the electron configuration is 1s2, 2s2. All right, then we skipped over to carbon. All right, and it has 6 electrons, so it goes up to the 2p. Remember, you're starting down at the bottom and you're putting them in 1, 2, 3, 4, 5, 6. 1s, 2s. When I draw the 2p, I'm going to do it down here, I need to draw all 3 boxes. All right, even though I'm occupying one of them, I'm going to draw all 3 of them because they come 3 at a time. So 1, 2, 3, 4, 5, 6. Now, generally, these would be written all in a line for the orbital diagram. Okay, that's what we're doing, orbital diagram. This is electron configuration. Oops. All right. Sorry about that. There we go. We would generally do the orbital diagrams all in a line, but I'm kind of running out of room here. The electron configuration is 1s2, 2s2, 2p. Sorry about that. 2p2. All right. Do a little erasing. Now, if you had a tough high school course or you've had a little bit more chemistry, we could do this, and I'm just going to do that for the benefit of those people. For carbon, I could write the electron configuration this way: 1s2, 2s2, and then you could do some, there are 3 p orbitals. How do we distinguish between them? They are oriented around each axis in 3-dimensional space. Okay, so you could do something like this, but nobody ever does that. Not really, but that is technically what we're doing. Okay, I'm going to introduce a few terms here before we leave these simple examples, and this is very important. All right, all of chemistry and understanding it hinges from here. This is why I'm starting here. I'm starting here because it's less mathematical, and all of the language, how the compounds come together, what their properties are, everything hinges from how these electrons are arranged. Okay, so it's very important what we're doing here. A couple of things I want to talk about. So I'm going to go ahead and just rewrite this the way it should be done. All right. But you do need to understand that when I write this electron configuration for carbon, even though we'll lose the orbital diagrams, remembering that these electrons are one at a time is important. All right, so carbon has 2 unpaired electrons in its ground state electron configuration. Ground state means your home spot. Okay, no electrons have been excited to other energy levels. The ground state, the lowest energy level state of the atom. So carbon has 2 unpaired electrons. Beryllium has 0 unpaired electrons. Lithium has 1. Helium has 0. All right, so this idea of how the electrons are arranged in the orbitals, not as apparent in the electron configuration. So you can't just forget about the orbital diagrams, because this unpaired electron business comes into bonding, which we're going to get into after we do the atom. So that's important. The other absolutely most important thing to take away from this whole exercise is the concept of valence electrons. All right, valence electrons. And I'm going to erase this carbon business at the bottom so that I can put the definition, what's in your notes, so I can put the definition for valence electrons down here at the bottom. Okay? And you probably want to put it in your notes with a big box around it. Valence electrons are the electrons in the outermost shell. So we'll talk about these examples before we leave them, and then we'll do some more examples. All right, and this will not come into play until we enter the 3Ds, and any unfilled orbitals. Now, the good thing is that this valence electron business is on your periodic tables, but you still need to understand where it comes from. All right, so back to helium. Helium only has one shell, so it is the outside shell. So helium has two, whoops, I'm going to write the valence electrons over here. Helium has two valence electrons. Lithium, the outermost shell, is the second shell. So this is an inner shell, this is the outermost shell, so lithium has one valence electron. All right. Beryllium, outermost shell, second shell. There are two electrons there. Beryllium has two valence electrons. All right. Carbon, outermost shell is the second shell, so we're going to add together the electrons that are in that outermost shell, and so carbon has four valence electrons. Now, before we leave this, didn't mean to be that big. Before we leave this screen, and I erase 4, I want you to look at your periodic tables. Find lithium. Helium's a little weirdy, so we'll skip helium for now. Lithium is in which column of the periodic table? Very first column on the left. At the top of that periodic table I gave you, I have written in some A and B numbers. What is the number that's followed by an A written at the top of lithium's column? It's 1A. Everything in the 1A column, this column right here on the periodic table, has one valence electron. All right, we'll see that as we go through some more examples. Beryllium, what column is it in? It's in the next column, the second column, and at the top of that column is written 2A. That means that every element in this column it has two valence electrons. Now, having the same number of valence electrons and, as we will see, in the same type of orbital makes their chemistry very much alike. So we call the columns families. Just like families are very much alike, these elements that are in these columns are very much alike because they have the same number and type of valence electrons. Carbon. Find the column carbon is in. It's over here. Right here. And at the top of that column there is a 4A. All of the elements in this column have 4 valence electrons. And they're in the same type of orbitals. They're in S. There are 2 in an S and 2 in a P. That makes their chemistry very similar, even though column 4 of the periodic table probably has the most diversity of any column. And we'll talk about that when we start talking more about the periodic table. All right? So let's do some more examples. So I need to get the big eraser out here and just erase away. And we're going to do, we're going to drop the orbital diagram soon because it just takes up too much room and time. And we'll leave our definition for valence electrons down there at the bottom. Okay? So there we go. All right. So remember, I cannot click on electron configuration orbital diagram. I bet you can do that. Why don't you try it? Pause while we have it up. And write the orbital diagram and the electron configuration, and that'll be the first one I do when I go back to writing. Okay? All right, picking back up. We're now at the end of the second row of the periodic table, and we ended the second shell. Now that won't be true exactly in all the other rows, but it does tell me after 2P, I'm going down to the third shell. So I know, regardless of whether or not I have that arrow on the left, that I'm in third row. And I'm not in the P territory. I will make this obvious, and it's in your long form of the periodic table. These first 2 columns are the S block, so I am dealing with S orbitals. These guys down here that are sandwiched in And I didn't mention why those were there. These are the two rows that generally are at the bottom of a periodic table. And the reason that we put them at the bottom of the periodic table is because we take them out. They're elements we don't encounter very much either. And put them at the bottom so the periodic table fits better on a piece of paper. That's the reason why this is the real form of the periodic table. Anyway, this is the F block, so we're dealing with F orbitals. When we get to this region of the periodic table, we're dealing with D's, and when we get to this region, we're dealing with P's. All right, so the periodic table tells me I don't even have to have a box diagram. When I get to the end of the second row, and I'm done with the P's, I'm now going to the third row, because, you know, we're a left-to-right reading society. I'm in the S, so I know I'm going to do 3S next, because I'm on the third row, I'm in the S block. So when I click on sodium, which has 11 electrons, I am going to end in the 3s. So if you're counting it out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right? So there's the orbital diagram for sodium, and we'll write it when we go back to writing. Magnesium, we're going to fill up that 3s. We're on the third row, still in the S block. All right? So it ends in 3s too. Now, without me having to look at that arrow, which you'll always have it, I am still in the third row, and I'm having to move over to the P block. Aluminum has 13 valence electrons. All right, so I clicked on it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Next is 3P, 13. And as we go across the P's, we will increase one at a time, and then we start pairing them up till we get to the end of the third row. And we have filled up the 3P. Now, this is where you get the first little weird filling. The order is weird after this point. Should be the 3D, right? Because on your diagram, they're actually connected by a line. But the periodic table tells me I'm at the end of the third row, and now I'm going to be in the fourth row, and I'm in S territory before I get to this D territory. All right? When I can write, I will explain why that the D's are 1 off the row and F's are 2 off the row. So before I fill up the D, I'm going to fill up the 4S. When I get to potassium, I don't have all these atomic numbers memorized. It has 19 electrons. Okay, so when I click on potassium, those 19 electrons will end in the 4S. Potassium is a fourth row element, so its outside shell has to be the fourth shell. The elements in the third row are third row elements, and their outside shell is the third shell. Elements in the fifth row, their outside shell is the fifth shell. Elements in the sixth row, their outside shell is the sixth shell. I told you, it's all connected to the periodic table. After potassium comes calcium. We fill up the 4S. And now, your arrow on the side, or if you're following on this periodic table business, we have now come to the 3Ds. And we put our first electron in for scandium, and then titanium, and then vanadium. And I'm going to stop there, okay? And then I'm going to come back and do some more, because it gets a little weird after this point, but I want to go back to writing and do some orbital diagrams and some electron configurations, cement idea about valence electrons, and so on. All right, so we ended before, when we were doing this business before, with carbon. So I told you that neon would be the first one we would do. So I'm going to draw neon's orbital diagram right here. 1s, 2s, and I know, because it's on the second row of the periodic table, that it is going to end with the 2p's, and its 10 electrons go in these boxes. So this is neon's orbital diagram. All right. Its electron configuration for neon is 1s2, 2s2, 2p6. All right, and this is neon. All right. So, question, how many unpaired electrons does neon have? 0 unpaired electrons. All right. How many valence electrons does neon have? Outside shell here. Maybe a little easier to see on the electron configuration. Second shell is the outside shell, so it's all of the electrons in the outside shell. So it has 8 valence electrons. Now, look at the top of the column. that neon is in, and you see that there is an 8A written there. Now I skipped helium before. Helium is put in the noble gas column not because it has 8 valence electrons, but because it fills its outside shell, the first shell, which makes its chemistry like the other noble gases. You will see some periodic tables where helium is put in column 2A, which its electron configuration matches those other elements in 2A, but because of the fact it's small, fill the outside shell, it's a little bit of an exception. Hydrogen is another exception. Both those elements on the first row, they're the smallest elements known, also probably the most, hydrogen is the most abundant element in the universe. They're just a little different because they're so small. All right, moving on. Let's do a few of the elements in the third row, and then we'll end with vanadium. And I need to show you a shortcut soon because those diagrams, the orbital diagrams, are going to get to be very tedious. All right, why don't we try magnesium? We're going to do an orbital diagram. We've already clicked on it, and we're going to write its electron configuration. So if you want to try that, just pause now and come back. I'm going to go ahead and do that right here. This was neon. And then before I leave neon and magnesium, I'm going to show you another shortcut. All right, so magnesium, orbital diagram. I know it's a third row element, and it's in the S block, so I know I'm going, oops, hold on. Let me make those, maybe bring it all over just a little bit. Okay, so magnesium. Okay, so this is my 1s, my 2s, my 2p, and my 3s. All right, so magnesium has 12 valence electrons, and all of them are paired, which is generally that's not true for the fact that it's an even number, because when you have the D's and the P's and the F's, you put them in one at a time, so you can't go by that. But so you have to think about it in terms of how these electrons fill the boxes. So this is magnesium, and let's write its electron configuration: 1s2, 2s2, 2p6, 3s2. All right, so 0 unpaired electrons for magnesium. They're all paired. And how many valence electrons? Third shell is the outside shell, so it has 2 valence electrons, just like the top of its column says. Okay? Now, shortcut before we leave neon and magnesium. When you write the electron configuration, unfortunately there really are no shortcuts for the orbital diagram. When you write the electron configuration, I can use, and I can only use, these guys here. I look for neon. It's at the end of the second row. I can use the noble gas, those are the guys in this last row, as essentially the rows before it. So before neon, which is a second row element, there's the first row. Helium ends the first row. So I am going to use helium as a depiction of the inner core for neon. And then its outer core, or its outside shell, its valence shell, is there. All right? Magnesium is a third row element. The noble gas that ends the second row is neon. So I am going to use neon to depict the inner core of magnesium, and then I'll write its outside shell configuration. Now the advantage of doing this is it's much easier to see valence electrons, and it's a lot shorter. Okay? All right, let's do some more examples. Right, because we haven't got up to vanadium yet, and we're going to do it. We're not going to do every one. We're going to skip a few, but we're going to do a few more of these. Okay, and then we're going to show you some weirdnesses, and then we're going to end this lecture by doing a little bit of practice in the notes. Okay, after magnesium, let's go to phosphorus. All right, so try phosphorus, orbital diagram and electron configuration. Okay. Coming back to us, phosphorus has 15 electrons, third row element. So I know that it's going to have all of the second shell filled in terms of an orbital diagram. And by when I finish the third row, I'm going to drop the orbital diagrams. It just takes up too much room. 1s, 2s, 2p, 3s, and the 3p, which I'm going to have to put down here. Okay, so this is phosphorus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Orbital diagram. Electron configuration. We'll do the long form and then we'll do the abbreviated noble gas form. 1s2, 2s2, 2p6, 3s2, 3p3. All right. Shortcut, phosphorus, third row element, noble gas that ends the row before it, neon, in brackets, and then that third row configuration. So essentially you're writing down its row. All right, so phosphorus is on the third row right here, so I'm coming back to the beginning of its row, 3s1, 3s2, 3p1, 2, 3. All periodic table based. How many unpaired electrons does phosphorus have? You have to think about the orbital diagram. 3 unpaired electrons. How many valence electrons does phosphorus have? 5 valence electrons. What is the number at the top of the column that phosphorus is in? 5a, just like nitrogen. 5 valence electrons. All right? Next one we're going to do is argon, and then we'll do scandium. Yes, argon and scandium. So if you want to stop and try those on your own, I'm going to erase and do those, and you can come back. When you come back, you'll be starting up right where I am. Okay, so I said argon has 18 valence electrons. It ends the third row. So we're going to do a 1s and a 2s and a 2p and a 3s. Oops. And a 3s and a 3p. All right, so putting those electrons in, 1, 2, 3, 4, 5, 6, 7. I just always do it this way. 8, 9, 10, 11, 12. That's the 1s, the 2s, the 2p, the 3s, and the 3p. 1, 2, 3, 4. So there are 18 electrons. And I am going to drop these after argon. Electron configuration, long form, 1s2, 2s2, 2p6, 3s2, 3p6. Shorthand, third row element, noble gas that ends the row before it, right here, neon. So neon, last time I'm going to use neon, 3s2, 3p6. Now some students at this point say, well, couldn't I just write argon for argon? No, because it doesn't show how many valence electrons it has, and so on. So how many valence electrons does argon have? 2 plus 6 is 8. 8 valence electrons. All electrons are paired, so it has 0 unpaired electrons. All right? Dropping orbital diagrams after this point. You'll have your diagram. You can click on it online, and so on. And we're going to do some more of that when we go back. All right, erasing. Then we're going to do scandium. Now we'll be able to do maybe do 2 elements at a time because I'm not doing the orbital diagrams anymore. All right, so scandium, electron configuration. It has a total of 21 electrons. It is a 4th row element right here. So after 4s comes 3d. The d's are 1 off the row. So if you're on the 4th row, it's 3d. If you're on the 5th row, it's 4d, and so on. The f's are 2 off. So when I'm on the 6th row of the periodic table, this is 4f. When I'm on the 7th row of the periodic table, this is the 5f. So that's what you have to remember if you're just using this to do the electron configurations. Okay, back to scandium. Long form, 1s2, 2s2, 2p6, there are the first 2 rows. Reading the 3rd row, 3s2, 3p6. All right, and now I'm up to argon, and so that's going to be my shortcut. After argon, after the 3rd row, 4s2, 3d1. Oops. Now, that little one up there. This is the first time, let me put that outside shell on there. The row it's on comes after the noble gas that ends the row before it. This is the first time we have encountered our full valence shell, valence electron definition. Electrons in the outermost shell, which in the case of, this is scandium, in the case of scandium is the fourth shell. So those count. And, which implies adding, any unfilled orbitals. This D is not full, and I'm talking about the whole D level, essentially. 2 plus 1 is 3. Scandium has 3 valence electrons. It has 1 unpaired electron. Okay, go back to the website and click on it to be sure of that. 3 valence electrons. What is the number written at the top of the row scandium is on? 3b. These elements that are in the middle, actually both these groups that are in the middle are called transition elements. These are transition metals. So I always work in a lot of periodic table stuff when I do electron configurations, so that when you do get to the periodic table chapter after this one, it's really not a lot because I've worked so much of it in. And these are the inner transitions. Okay? Transition metals are different. That's why they have B's instead of A's. Okay? You'll see as we go through them in a moment that they are weird. Okay? All right, vanadium. Last one we clicked on. All right, 2 more electrons than scandium. So I'm just going to do the shortcut. Argon ends the row before vanadium. Vanadium's on the 4th row. So now I'm going to read the 4th row until I get to vanadium. 4s2, 3d, remember it's 1 off, 1, 2, 3, 3d3. So how many valence electrons does vanadium have? 5. 2 plus 3 is 5. Outermost shell is the 4th shell. The D is still not full, so we're going to use those as well. 2 plus 3 is 5. How many of those are unpaired? Now you have to think about how they're arranged in the boxes. 3 unpaired. The D's go in one at a time. That S, they're paired. Okay? All right. Let's go back to our website. And let's look at some weird things that happen, and we're just going to do a few more, okay? Now, you are not going to be responsible for these quote-unquote anomalies, but we stopped at vanadium. Now, watch the boxes up here as I click on chromium. Crazy! Back to vanadium. 4s2, 3d3. When I click on chromium, element added to iron to make steel, its electron configuration, it still has the right number. It's just that it would rather promote electrons from the 4s up into the 3d, so everybody has their own bathroom. Oh, I'm sorry, their own bedroom. 6 unpaired electrons. All right. If you told me the electron configuration was 4s2, 3d4, that would be fine. But I'm showing you that it's in reality it's not. When we go to manganese, things are okay. And then on to iron and cobalt. Now everything is exactly the way it should be. Now as we notice that chromium was 1, there are 10 electrons. There are 10 elements here in the D block because there are 5 d orbitals, 2 each, so 10 elements representing the d orbitals. As I get close to the midway point is when weird things happen, and when I get close to the end, weird things happen. Nickel's fine. Now watch copper. All right, let's stay here on copper for a moment. Copper would rather fill that D and leave the 4s half full. What is the number written at the top of the column that copper is in? It's 1b. That number is showing that it only has 1 valence electron because the outermost shell here is the 4th shell. And now the D is full, so we're not going to count it. So copper has 1 valence electron. Zinc has 2. The D is full, so we're not going to count it. The outermost shell is the 4th shell, so we're only counting those. All right? So 2 valence electrons. We'll do a couple of those when we go back to writing. Cat on my lap. Now, fourth row, we're still in the fourth row, and we have encountered the P block. So now we're going to start filling up the P's, and nothing weird ever happens in the P's. So we fill them up one at a time until we get to the end of the row with krypton, and the 4p is full. The periodic table tells me the next row I'm going to is the fifth row, and I'm in S territory. So the next element orbital I'm going to fill up is the 5s. I can now use krypton in my abbreviations. Strontium 5s2. And then the periodic table tells me I'm in D territory, and it's one off the row, so it's going to be 41, 42, and then even more strange things happen in the fourth row. Don't worry about it. All right, so we're going to do a couple more in the third row and a couple more in the fourth row. Now what I want to do is we get to xenon at the end of the fifth row. We filled up the 5p. The periodic table tells me that when I go to the sixth row, I'm in the 6s, so I'm going to fill that up first. Now, let me show you something that you don't need to worry about too much. Lanthanum. When these two rows are peeled out and put at the bottom, sometimes lanthanum heads up those rows, that first row at the bottom, and sometimes it does not. Let me show you why why some periodic tables leave it in the D's. I'm going to click on it. And then I click on cerium. And then I click on praseodymium, and things are as we would assume. All right, so if you tell me that for cerium, the electron configuration is xenon, which ends the row before it, 6s2 for cerium, 4f2, that would be fine. Okay, if you told me that lanthanum was 6s2, 4f1, that's fine. I'm showing you in reality that there are some strange things that happen. And the reason why is, as this diagram depicts, when you are down here in the first, second, third shell, the energy levels are rather far apart. When you get up here to, more and more energy levels, they get closer and closer together. So it's easier for electrons to move between energy levels, and you see all sorts of chemistry resulting from that, okay, because the energy levels are so close together. All right, so sixth row, when you get to the F's, you're 2 off the row. 6s2, 4f, all the way across. How many F orbitals are there? 7. How many elements are here? 14. All right, lanthanum heads up this row, and the periodic table I gave you puts lanthanum at the bottom, heading up the row, because this row at the bottom is called the lanthanides. This row at the bottom is called the actinides, for actinium. Lanthanides and actinides. All right, and this is where all your radioactive elements are. Lots of radioactive and man-made elements, for that matter. After the F's, we're in the sixth row. We're in the D territory, so now we're one off the row, so it's 5D. Okay, and so on. And we're not going to do hardly any of these. And then when I get over here to P territory, it's 6P, and so on. All right, seventh row, same kind of thing. Remember, after the fourth row, fourth shell, it repeats. Okay, let's go back to writing. And do a few more, and we're done. Okay, and we're going to go back to the notes and finish up with some examples that are there. So I'm just going to do about 4 more, and then we're going to go to the notes to finish this up. Okay, we ended with vanadium. So let's do, and you can stop it and try this, electron configuration for gallium with 31 electrons. It is in the fourth row of the periodic table, gallium. If it's in the fourth row of the periodic table, it is going to, its shortcut is going to be argon. And then what is after argon on its row, read its row, 4s2, 2, 3d10, because we go all the way through the D's, and then it's 4p1. Okay, so when you're in the S's and P's, it's exactly the same as the row. So if you're on the fourth row and you're in the S territory, it's 4s. If you're in the P territory, it's 4p. The D's are full. We're not going to count them when we count valence electrons. 2 plus 1 is 3. Outside shell, there are 3 valence electrons and 1 unpaired electron for gallium. Gallium is a strange metal, melts in your hand. All right, after gallium, let's do bromine. electron configuration. Still fourth row, so argon. So that should be like, okay. And then read its row, 4s2, 3d10, 4p5. How many valence electrons does bromine have? 7 valence electrons. All right, before I leave gallium, and I'm going to do one more actually. Before I leave this page, we're going to do one more thing. Another little shortcut, if you will. All right, let's do strontium. Fifth row element. So I am now going to use krypton as my shortcut. And it's going to be krypton, fifth row, 5s2. It's in the second column. 2 valence electrons and zero unpaired. Okay? We're going to do a Lewis dot structure for these elements. And we're not going to do Lewis dots for elements too much. We're going to do them when we put them in together and make compounds. But it is a way of showing the valence electrons. So gallium has 3, and the way that we do it is we put 1 dot on each side of the symbol to depict the valence electrons. Bromine has 5, so we're going to do 1, 2, 3, 4, 5. Strontium has 2, does not matter where you start, as long as you put one at a time and then pair them up. Okay, so those are Lewis dot diagrams for elements, and it shows valence electrons. All right, let's erase and do just a couple more, and then we're going to do those practice in the notes, which is where your quiz questions come from, and that'll do us for the lecture 6. All right, we just did bromine. I'm sorry, we just did strontium. Let's do palladium. Palladium, PD. It's in the 5th row in the D block. Palladium. So 5th row means I'm going to use krypton as my shortcut. And the row is 5s2, 4d, now just count over. 1, 2, 3, 4, 5, 6, 7, 8. 4d8. Oops. Now I picked palladium for a reason. The reason I picked it is because if you notice in the middle of the transition metals, there are 3 columns that have an 8 over them, 8b, and palladium is in one of those columns. If I used my valence electron definition exactly, palladium would have 10 valence electrons. Okay? Well, it doesn't act like it has 10 valence electrons. It acts like it has 8. And that's just something that you can take from the periodic table and accept. I've often given students credit for saying both 8 or 10 in the case of an element like palladium. Ruthenium, 2 elements back, also has 8 above it. Well, let's just do its electron configuration quickly. It'll be krypton, and instead of, it'll still be 5s2, 4d6. Now it's a little more obvious why it has an 8 at the top. Okay, 4d8, 4d6, because 6 and 2 is 8. I'm just pointing this out, 8 valence electrons, okay? And the row in between, which would be rhodium or cobalt or iridium, all of those elements have a 5s, would have an s2, 4d7, so technically they'd have 9. I'm pointing out that they act like they have 8, and we're going to leave it at that. When you do these dot diagrams, you never put more than 8 around it. Kind of like fills it up to put the 8. 1, 2, 3, 4, 5, 6, 7, 8. We don't generally put more than, although, as we'll see when we do dot diagrams, these elements can have more than 8 electrons around them. Anyway, getting ahead. All right, to finish us off, let's just do osmium. No, let's do dysprosium, element number 66. I did some of my graduate research on using dysprosium. Dysprosium, element 66. It's in the F block. We haven't done one of those. Let's just do that one to finish us up. All right, so you might have tried it on your own. Dysprosium is technically in the 6th row of the periodic table, so I'm going to use xenon as my abbreviator for the inner core, and then I'm going to read its row. 6th row of the periodic table, 6s2. After the s's come the f's, and dysprosium is in the f's, and the f's are 2 off, so it's going to be 4f, and I'm going to count over, starting with lanthanum. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4f10. Now, with the F block, you see that there are no numbers. There are no numbers written at the tops of these columns. Their chemistry is so different from the other elements. They are very big. They have lots of valence electrons, if you will. We will not be drawing dot diagrams for them. Okay, the numbers of valence electrons are not indicated on the periodic table, but I just wanted to do one of those. All right, let's go back to the notes and finish off with the examples, and this video will be done. All right, so you'll notice that the electron configurations and orbital diagrams really have to be experienced in the way I just did it. So that's why there's very little explanation here. And you really have to just go to the periodic table and do it the way we've done it. All right, so let me do a screenshot. Go back to notebook. All right, so now we'll be able to do these questions, and I'll be able to write the answers. How many 3D electrons are in an atom of each element? So really what you need to do is write the electron configuration to figure this out, right? So iron, 3rd row element, so we're going to do neon. 3s, I'm sorry, it's a 4th row element, so we're going to use argon. My bad. All right, so argon, 4s2, and really you can write the electron configurations and figure it out that way, but some of you might be getting this whole periodic table thing. If I pinpoint where iron is, it is in the 3D. 1, 2, 3, 4, 5, 6 over, so it has 6 3D electrons. Zinc, find where it is on the periodic table. Its electron configuration would be argon, 4s2, 3d10, but I'm telling you, you can do this from the periodic table. You see that zinc is in the 3Ds and it's at the end, so it has to have 10. This one has 6. Potassium is at the beginning of the 4th row. You haven't encountered the 3Ds yet, so it has 0. Arsenic is after the 3Ds, so all of the Ds are full. It has 10. All right. Now, here comes my favorite part. This tells me exactly what element it is. 3rd row, 1st column of the S block. This element is sodium. Sodium. The elements that have symbols that do not correspond to the names are the ones we've known the longest because they come from their Latin names, and sodium was called natrium. 5s2, 4d10, it's in the 5th row at the end of the Ds. So this element is cadmium. 6th row, 2nd column of the S block, this element is barium. And 5th row ends in the 3rd column of the Ps. 5th row, 3rd column, 1, 2, 3. This is antimony or antimony. So the electron configuration completely tied to the periodic table. All right. Now, to finish this lecture off, I'm going to go back to the notes. There's a little bit more. I want you to go back to this periodic table And what I am talking about in that next paragraph is I'm expecting you to get a blank periodic table, go to Sakai under Resources, and there is a link for periodic table, all kinds, and you can print off some blank periodic tables. And you need to identify on your blank periodic table where all of these groups are. We've talked extensively about the blocks, S block, D block, P block, F block, okay? And you need to identify these because you need to know them. As you might have seen when we were doing the electron configurations, I was throwing those names out there a bit. It's part of the language of chemistry is knowing the names of the groups of the periodic table. Metals, very important as we move into bonding. The majority of the elements in the periodic table are metals. There aren't that many nonmetals, and this is going to be very important when we start to distinguish between types of bonding. Okay? So you need to know where they are. So know all of these groups. Identify all of these groups on your blank, one or two blank periodic tables. All right, so that's what that little paragraph is about. All right, so this tells me everything I need to know. I know that it is a 6th row element. All right, so it is a 6th row element because it ends in a 6. I know that it's on the S block because of that S right there. And I know that if this is the valence shell. So what's left off here are the noble gases. All right, so if it's a 6th row element, the noble gas that should be here is krypton. And if it's a 3rd row element, the noble gas that should be here is neon, and so on. Okay, and this should be 4th row element should be argon, and 6th row element again would be krypton. All right. All right, so that's left off, and what we're showing here is the valence electron configuration. So what row is it on? It's on the 3rd row. What block is it in? It's in the P block because it ends in a P. How many valence electrons? 2 plus 3 is 5. The outside shell is the 3rd shell, so 5. Oops, skip that one on the 1st row. How many valence electrons? 2. What row is it on? 4th row. Largest outermost shell is the 4th shell. That's the row it's on. How many valence electrons? Block D, ends in a D. Number of valence electrons? 6. The D isn't full, so I'm going to add those together. Okay? What row is it on? 6th row. What block is it in? The F. And how many valence electrons? 7, technically, because the F isn't full, so we're going to add those two superscripts together. Okay? All right, now, to get us ready for lecture 7, we are going to do a little bit about metals versus nonmetals. Okay? So we're going to go back to the notes just briefly so I can get us. Now, what I'm saying here is that numbers of valence electrons, very important. What type of element it is also very important because metals are losers and nonmetals gain. Nonmetals always gain to make 8. Now, the metals don't always lose all of their valence electrons. They're losers. But the ones we're going to start with do lose all that they have. Okay? So we're going to start with the predictable ones. The ones that are not predictable are the transition metals in the middle. There are 3 transition metals that are very predictable. All right, so we're going to finish off with this idea so that when we start up with lecture 7, okay, we are going to, just kind of scrolling ahead, we're going to talk about some periodic trends. But this idea of who loses, how many you lose, how many you gain, we're going to get into charge, which we haven't done yet, is going to get us ready for ionic bonding. Okay? So I know we've done a lot. Let's just do a little bit more. You can always come back to this point at the beginning before you do lecture 8 and review some of this these ideas. Okay? All right, so let me do a screenshot. All right, so which elements would you expect to be losers? Well, they have to be metals. So if you have to, go back, go to your periodic table that you have pause and identify where those metals are. But that's what essentially you're asking. Which of these are metals? Okay? Potassium is a metal. Sulfur is not. Fluorine is not. Barium is a metal. Copper is a metal. So knowing which are metals and nonmetals is the beginning of understanding ionic compounds, because they are going to be metal and a nonmetal. All right? Now, this is the first time we have encountered charges. Up to this point, we've been dealing with atoms, and now we're going to deal with ions. Remember, I said that if an atom had a charge, we didn't call it an atom anymore, we called it an ion. So if I am a metal, I form a positive ion. Now, why is that? I want to spend some time, and that's one of the things I'm doing here in this last bit of this lecture, is making sure that you understand where these charges come from. All right, sodium is a metal. How many valence electrons does sodium have? Look on your periodic tables. The number at the top of its column is a 1. So sodium is a metal that's going to lose 1 electron. Now, before sodium lost anything, sodium had 11 protons and 11 electrons when it was the neutral atom of sodium. The chemistry of sodium is completely dominated by the fact that it has 1 valence electron and it's a metal. Okay? So it's going to lose that 1. And so now protons don't change, but electrons can change when I have a charge. So it's 10 electrons because I've lost 1. 10 negatives and 11 positives give me that positive 1. All right, let's go on. You'll get this. Strontium, metal. How many valence electrons? Let's first write down what it had to begin with. 38 protons, 38 electrons. It's a metal. How many valence electrons does it have? 2. It's going to lose those 2. So the protons don't change, but now I'm going to have 36 electrons. 38 positives and 36 negatives give you the 2 plus. So for metals, the number of electrons you lose, you end up with that many positive charges. Oxygen, nonmetal. Nonmetals are much more predictable. They all gain to make 8. So they take the valence electrons they have and they add on to make 8. So it had 8 protons, 8 electrons. It has 6 valence electrons. So it needs to gain 2 to make 8. So it'll still have 8 protons, but now it has 10 electrons, 8 positives, 10 negatives, gives me a 2 minus ion. So nonmetals, the number of electrons they gain gives you the negative charge. So metals, losers, positive, and we have a fancy science word for that. We call it a cation. Okay? Nonmetals gain. So therefore they're negative. They're gaining negative things. These guys are losing negative things. That's why they end up being positive. And we call negative ions anions. Anions. Okay? Let's do cobalt. We'll get some erasing done here. And then we'll move on with these examples. Let's just get this all cleaned up. And do a little scrolling. There we go. Okay. So cobalt had, where are we? There we are, 27 protons, 27 electrons. Looks like I lost 3, so I have 27 protons still, but now I have 24 electrons. Okay. Charge of each ion. There are 2 ways you can do number 3. You can look at scandium and see that it had 21, now it has 18, it lost 3, so it has a plus 3. Or you can begin the thinking that you need to have, and that is you're looking at the periodic table, you see that it's a metal. Scandium is one of the transition metals that's predictable. It has 3 valence electrons, it loses those 3, so it's going to be a plus 3. Okay? Tellurium, non-metal. Actually, it's kind of a metalloid, but it has 54 electrons according to this. It had 52, so it has gained 2, so therefore it's a negative 2 charge. But another way to think about it is tellurium, nonmetal territory, has 6 valence electrons, gains 2 to make 8. All right, you're not going to be given this information most of the time as we get into bonding. You have to be able to look at the periodic table and predict. Nitrogen, nonmetal, has 5, gains to make 8, so it is going to form a -3 ion. It had 7 and now has 10, so -3. Barium, metal, has 2, loses them, barium with a +2. It had 56, now it has 54, so +2. All right? Okay, iron. So it's asking, is this part correct given the charge that's depicted here in each example? All right, iron has 26 protons. So right off the bat, looking at the periodic table, the protons never change. That is not true. Now I'm going to correct the ones that are false. This one's false. It had 26. That +1 says it lost 1, so it has 25 electrons. All right, 26 was the atomic number. It had 26 electrons before it gained that charge. It has a +1, so it lost 1. This is the correct number of protons and electrons. Cesium has 55 protons. That is correct. However, a +1 charge says that instead of 55, it should have 54. So it is also false. Selenium has 34 protons. So false again. This book likes to do 3 and 1 when it does trues and falses. 34 protons, and selenium with a 2- charge means it should have 36 electrons. It has 2 more than it had before. Lithium, this must be our true, 3 protons, that is correct. And if it has a +1 charge, it now has 2 electrons instead of 3. All right? Very important that you understand where the charges come from. Here we go. One more. 2 more questions and we're done. All right, and then down here at the bottom, I've got it. If you want to go and look at it, it's another source of information about the atom. Sometimes hearing it from a different perspective is very helpful. I've got videos linked throughout the notes to help you with a different perspective if you think you need it. All right, one more time. So now we're going to do that thinking that I was going through before. Fluorine, non-metal, gains to make 8, had 7, so it gains 1 to form a -1. Nitrogen, non-metal, has 5, gains to make 8, so it needs to gain 3, -3. Now, you might be asking, does it matter if I write it this way or this way? Nope, it does not, and you will see me write it either way. Magnesium, metal, 2 valence electrons, loses them, +2. Sodium, metal, has 1, loses it. All right. And now in number 6, we're going to do this one more time. We've already done some of these examples, and we're going to do this whole electron-proton thing. All right. So we just did fluorine above. We know that it forms a -1. The number of electrons instead of 9 should be 10 because it gained 1, and the number of protons, of course, doesn't change. In fact, I'm going to fill this column in because this is just the atomic number from the periodic table. Beryllium, 4. Bromine, 35. That never changes unless we're doing nuclear reactions, and we're not doing that. Aluminum, 13. And oxygen is 8. All right. The number of electrons is going to change because of the ion that these things form. Beryllium, metal, has 2, so it's going to form a +2. It had 4, so now it has 2. It had 4 electrons, now it has 2. Bromine, non-metal, has 7, gains 1, so it had 35 electrons, now it has 36 because it gained 1. Remember, in the neutral atom, the protons and electrons are the same. These 2 columns are not going to be the same anymore because we're talking about ions in this table, not atoms. All right. Aluminum, metal. Many students don't see that aluminum is a metal based on where it is on the periodic table. You know aluminum's metal. It's a metal you probably have the most experience with. 3 valence electrons. It's going to lose those 3. So instead of 13, it now has 10. Oxygen, non-metal, had 6, gains 2. So it had 8, so now it has 10. And that is going to finish us up for Lecture 6.